All right, so we did the first fundamental theorem. So we are going to be working on fundamental theorem part 2, which is actually, it's pretty connected to the fundamental theorem part 1. So we're going to start and we're going to define something called the area function. So area function is what's referred to as a of x right here. So I'm going to give you a definition kind of in words and then like an actual mathematical formulaic definition. All right, so this a of x right here, it represents the area under the curve, which we've been dealing with area under the curve for like a week or so now. So a of x is the area under our curve, and that's this specific curve right here, f of t. So the area under f of t from a, so now here's the part that makes it a function. A is a fixed point. It could be 2, it could be 7, it could be fixed anywhere we want. So it's the area from a to x. Now x is a variable. Okay, so a is a fixed number, x is a variable, so that's what makes this a function. So if I said like a of 3, it would be the area from a to 3. And again, a is some fixed number there. All right, so the actual formula that we can write down looks like this. It is the area under f of t from a to x. So we have f of t dt. The reason that we use two different variables here is we just don't want to get anything confused. We want to make sure we're keeping everything straight. So t represents the function along the line here. So notice this variable is t. This, of course, is still just a y. And then the x is whatever upper bound you're plugging in. So a, in every single problem, like this one right here, they fixed a 2. And then x is the upper bound. That's being treated as the variable of this function. Okay, so sometimes this is arbitrary. Sometimes we can actually find a formula for it. So if we're trying to find this area function right here. So a of x is written as the area starting at 2 and ending at some variable x under a function t cubed. Okay, so we actually can go through and find this formula now that we know the fundamental theorem part 1. Okay, so the formula works like this. You know, we take the antiderivative. So the antiderivative of t cubed, we have 1/4 t to the 4th. And then we are evaluating from 2 to x. Okay, so the way the fundamental theorem works, remember we plug in our upper bound and then subtract what we get when we plug in our lower bound. Okay, so we're going to simplify that up. So we get just a 1/4 x to the 4th, and then minus 2 to the 4th is 16, a fourth of 16 is 4. So what this represents now is if I wanted to find the area from 2 to 3, or if I wanted to find the area from 2 to 7, or 2 to 20, or whatever I wanted to find, rather than doing the fundamental theorem over and over and over again, what I do is I just take my upper bound, whatever it is that I wanted to plug in, and I sub it into this function. So remember one of our properties from earlier was that the area from 2 to 2 should always be 0. So let's check that out. If I plug 2 in right here, 2 to the 4th is 16. A fourth of 16 is 4. 4 minus 4 does in fact give us 0. All right, so this represents the area under the curve. So it's pretty quick and easy once you have a formula like that. Okay, so this next part is what's going to lead us right to the second fundamental theorem. So I want to find a prime of x. So now that I have this, I want to take the derivative. So if I multiply this power out, I have 1 and then x cubed. And then the derivative of 4, of course, is just 0. So I end up with x cubed, which, if you look carefully, x cubed is a very similar function to t cubed. All I did was just switch my variables. Okay, so here's the second fundamental theorem. We have, of course, a continuous function on an open interval, and we want a to be on that interval that we're talking about. So here's what we do. If we take the derivative of the antiderivative, what we end up with is just the original function, but with x plugged in this time. Okay, so this is going to seem a little bit strange. So here's what's happening. I start with a function. I take the area under that function, in other words, the antiderivative, and then I take the derivative. So basically what you're doing is you're taking the antiderivative and then you're taking the derivative. Those two processes cancel each other out. It would basically be the same as squaring something then square rooting it. You're right back where you started. Or multiplying by 7, then dividing by 7. You're right back where you started. So the only thing that ends up changing is my variable will swap out because this x will get subbed in, therefore changing everything to be in terms of x. So this is our second fundamental theorem. We're going to play around with it a little bit. First thing that we have here is what we call an initial condition, and that's just what happens if you plug in the lower bound. So we want to see the area function. If I take my area function, and I sub in A, which is my lower bound. So say I plug in A to A, that will always give me 0. Okay, so my initial condition means if I sub in whatever my lower bound is, because think about that, if you're looking at an interval and the interval doesn't have any width, it can't possibly have any area. Okay, so that's the initial condition. And then one thing to keep in mind there is that if you're looking at an area function and you are looking under, like, you know, in that little area between A and A, you're not going to be left with any area at all. So this is just that idea in words. So the area under f of t from A to A is 0. Okay, so again, that's this idea in words. Okay, so now we're going to do a little proof of the second fundamental theorem. And I don't want you to panic just because you saw the word proof. We're not doing like a geometry 2-column proof or anything. We're just proving why this ends up being the same as this. Okay, so we are going to start with this piece of it. Okay, so let's start with this. Okay, so we're going to do essentially the first fundamental theorem right now, just to get an expression for this. So remember before we've used a capital F to represent the antiderivative. So fundamental theorem says we take the antiderivative of f, which we're writing as capital F. We evaluate it from a to x. So we plug in the upper bound, plug in the lower bound, and subtract. So we get that. Okay, so that means this piece, which is just the inside piece right here, ends up being this. Antiderivative with x plugged in minus the antiderivative with a plugged in. So here's the super important part, all right? This right here, if I take the antiderivative and I plug in a, this is just going to be a constant. We don't know what the constant is. It doesn't matter what the constant is. The important part is that it is, in fact, a constant. Okay, so now to get this full expression right here, I want to take the derivative. Okay, so taking the derivative with respect to x of this expression right here means taking the derivative with respect to x of this expression that I have on the right. Okay, so remember that this represents the antiderivative. So if I take the derivative of the antiderivative, I land right back at the original function. My variable has just now changed to x. And then this is a constant. That's the important point that I wrote right here. So if I take the derivative of a constant, I just end up with 0. And so I do, in fact, end up with f of x, which is exactly what I had up here. Okay, so that's a little mini proof, I suppose. So our first example that we're going to look at, this capital F is defined as the area function starting at 0, ending at x under this function right here. So here's the tricky thing with this one, is that I can't find an antiderivative for this. So I'm basically just going to apply what the second fundamental theorem tells us. So f of 0, when I see this right here, that means I'm replacing the x, which is right there. So I am taking the area from 0 to 0 of this integrand right here. So now it doesn't matter at all what this function looks like. The important part is that I'm going from 0 to 0. If I have no width, I have no area, which means this just comes out to be 0. And that kind of goes with this initial condition right here. If you plug the lower bound into your function, you're guaranteed to get 0. No width means no area. So now f prime of 0, if we pay attention to this right here, the second fundamental theorem, if I take the first derivative, f prime of x, remember the derivative of the antiderivative just means you get the function, but with an x plugged in. So the derivative of this is just the square root of x squared plus x. All right, so if I want f prime of 0, I'm just plugging in 0 right here. And that, of course, will give me 0. And then I can do the exact same thing using the same formula, but this time for 3. Okay, so I end up with a 12 under the square root, and I can simplify that up to 2 root 3. Okay, so that's my first example. So now let's flip and take some some derivatives using the second fundamental theorem. So it says we want to calculate the derivatives. So I'm going to just make sure this is written right up here so we've got it in clear reference on the screen. Okay, so we follow our formula. If we are taking the derivative of the antiderivative, we just take this function and plug the x in. So this one's super easy, and there's some that you will see on the multiple choice section of the AP test that are just this easy, and it freaks people out because it's that easy. So here's when things change. Here's when it's not quite that easy, is when I have an upper bound that's not just an x, because this formula doesn't just have, or this formula has an x, this doesn't just have an x. So let's play around with it. Let's kind of take it piece by piece. So let's look just at this part right here. Okay, so I'm going to leave the d by dx out front, and I'm going to worry about cleaning up just this part on the inside. So let's do this first fundamental theorem. Take the antiderivative, plug in my bounds, then see what happens. So the antiderivative of secant tangent is just secant. Remember, we're trying to figure out what function gives me a derivative of secant tangent, and that would be secant. So secant of t, I'm evaluating it from 1 to x cubed. Okay, so keep that d by dx out front while I simplify up the inside. So I have secant of x cubed and then minus secant of 1. Okay, so now that I've completed that inside, I can work on taking the derivative. So take the derivative of this right here. It's going to require a chain rule. The derivative of secant, remember, of course, is secant tangent. So I have secant x cubed, tangent x cubed. I leave that nested function right in there while I'm doing the chain rule. And then because it's the chain rule, I have to multiply by my nested derivative. So times 3x squared. All right, and then minus, now secant of 1, I don't know what secant of 1 is, but I do know for sure that it's a constant. Okay, so that part's very important, and I know the derivative of a constant is just 0. Okay, so here's what I end up with. I get 3x squared times the secant of x cubed times the tangent of x cubed. Okay, so I want to compare these two examples here. This one had x as an upper bound, and so all I did when I took the derivative of the antiderivative was I just subbed that x right in here, and this is what I got. This one, because I had a fancier upper bound, not just an x, this ended up being this. Now, it's pretty close to what I have up here. I did take the x cubed and I plugged it in for t right here and right here. But the extra little piece that I have right here is like a correction factor. What that piece was, it was the derivative of the upper bound. And so you could technically consider the derivative of the upper bound to be here too. The derivative of x is just 1. You could technically always consider yourself to have a 1 out front there. All right, so here's a chain rule. This is going to be set up basically the same way, except this time we're going to have a set lower bound a, and we're going to write g of x. So we're going to have some sort of expression instead of just an x. And then if I have f of t here, it's very similar. I still take my function, and I still plug in my upper bound, but then later I multiply by the derivative of my upper bound. So that's exactly what I have here. Here's my function on the inside with the upper bound plugged in, and then here's g prime, the derivative of the nested function. All right, so let's try one now that we know the chain rule for the fundamental theorem part 2. Derivative of the antiderivative, I have a fancy upper bound. I start by literally just replacing the t with the upper bound. But then because it is a chain rule, I have to multiply by its derivative. So the derivative of 1 over x is negative x to the negative second. I can clean that up just a little bit. Okay, so that'll look something like that. It's not the neatest function, but that's really the best I can do. All right, so we're going to do a lot of comparisons down here that'll be super important for the AP test, because a lot of times they'll give you something like an area function, and you'll have to write down a whole bunch of stuff. Okay, so a lot of stuff similar to what we did in chapter 4, kind of showing like the increasing, decreasing maxes and mins and things like this. All right, so this is going to be a comparison between the area function and the original function. Okay, so if we look right here, this curve is f of x. We could also consider it to be f of t, doesn't really matter. And then this function represents how the area is changing. Okay, so this is our function f, this is our function a. Let's make that, I'm going to change this to a t, just so that everything's kind of matching with the notation that we have here. All right, so if we compare some different features, first of all, I'm going to just rewrite this just so we have it right in front of us. Okay, so just some comparisons from chart to chart. First thing I want you to notice is that whenever our function f is greater than 0, what we end up seeing is that a of x is increasing. Okay, so whenever f of x is positive, like physically up above the x-axis, that happens here and that happens here, you can compare it to my area function and see that my area is increasing. And right here, my area is increasing. So this, all that stuff that I'm writing is labeled on this picture, but I just want to make, kind of explain it and make sure it makes sense. So here's why we say that a of x is increasing. My function a is accumulating positive area. Okay, because remember, what a of x represents is the area function. It is the area under this curve from a to x. So if I start right here and I start moving over to the right up until this point, I'm picking up more and more positive area. So that should make sense that the area is increasing. So that's what happens down here. So then very similarly, we can say when f is negative, that means that a is decreasing. Okay, so like this piece of the graph right here, my function is below the x-axis, and when I compare that to my area function, the area is decreasing. So two different ways that you could think about that, similar to what I wrote in parentheses here. You could either think of your function as gaining negative area, and that would make you decrease, or you could think of it as losing area, like losing positive area. Okay, so whatever makes the most sense to you. Remember, we think of anything below the x-axis as negative area. So here I'm accumulating positive area, then I start accumulating negative area, which means my overall area would be decreasing. Okay, let's talk about maxes and mins. Okay, so my function a is going to have a local max, a relative max, whenever f switches from increasing to decreasing. I'm sorry, positive to negative, not increasing to decreasing. Whenever f switches from positive to negative, a is going to have a relative max, okay? That's when I switch from gaining positive area to losing positive area. So that would be the largest that the area is going to be in that general time, because I'm picking up area, then I start losing area. So this is going to be a max for the time being. A has a relative min at the exact opposite point, whenever f switches from negative to positive. Okay, that happens right here. I'm picking up negative area, which means my area is decreasing. Then I start picking up positive area, which means after my area function was decreasing, it turns around and starts increasing. So that is going to be a local min. The really important relationship to remember is that f of x is the same as a prime. So any relationship that you have between a function and its derivative, you're going to have that same relationship here. All right, so you can think of this as being like the original function and think of this as being the derivative function. Okay, so think of this as being the original function and think of this as being the derivative function. And then all the same relationships that you had in chapter 4 apply here. So when your original function is increasing, your derivative is positive. When your original function is decreasing, your derivative is negative. When your original function switches from increasing to decreasing, you've got a 0 here. I'm sorry, when you have a local max, that means your derivative switches from positive to negative. When your function has a local min, your derivative switches from negative to positive. So that same chart that we've made a whole bunch of times, you can see all those relationships here. All right, so that's it.